This is Dr. Carroll. For today's video, we're going to explore the efficiency of hashing. Okay, so hopefully you've watched the other hashing videos. So let's start by talking about insertion. So to insert, we first hash the key and then we insert the item into the hash table. If the hash function is a good hash function, watch the other videos to get the definition of that, then it takes order constant time, which is awesome. Okay, so that's hashing if it's a good hash function. Then the other part is if we're inserting using separate chaining, then we just insert the item onto the front of the list. We're still at order constant time. Awesome. But if we're inserting into if we're using open addressing, then we need to find an open location, and that's going to depend on the load factor to determine where we're going to insert that. Now, this is average case scenarios, or even for separate chaining worst case, except that for really the worst case is if we insert an item, we may need to rehash the entire table. And that would require going through each of the n elements and rehashing them. That'd be the ultimate worst case. Now let's move to searching and deletion. And deletion, of course, you got to search for it before you can delete it. So the efficiency really depends on if the success is successful or not. If it's unsuccessful, it's going to generally take more time to look at that. And these are going to depend on the load factor alpha, which, as you'll remember, is the ratio of the current number of items in the hash table divided by the size of the hash table. In general, it's a measure of how full the hash table is. Okay, so let's talk explicitly about the approximate average number of items visited. Okay, and so we'll start by talking about unsuccessful searches, and then we'll move to successful searches. So for a unsuccessful search on separate chaining, we're going to have to go through the entire list to be able to try to find the item that we're looking for. And if you'll remember, alpha, the load factor, is the average length of the list. So on average, it's got to go through the average length of the list to exhaust it and say it's not here. That means it doesn't exist. And so it's alpha. It's going to take alpha comparisons to see that. And I have a little graph here to show this. So unsuccessful searches, here's our load factor from 0 to 1. Okay. Hopefully it doesn't get much higher than 1. And then on the y-axis here, the number of items visited. As you can see, an unsuccessful search, it's just going to, as the load factor increases, the number of items visited in general is going to increase as well. Okay. Now, and so as it increases, we want to keep, we're using hash tables for their awesome efficiency. So we need to keep that load factor down. And notice how it's the load factor and not the table size. I would have thought initially that it would depend on the table size, but it does, because the load factor depends on the table size. But the load factor is the governing statistic here that we need to keep our eyes on. And so for a separate chaining, if it becomes greater than about 1, then we're going to resize the hash table. We're going to rehash it. Okay. Now let's. And consequently, when starting, if you have a guess of how many number of items you're going to put in there, then just start with that size, because you don't want to have to rehash. Okay. So for linear probing, I'm not going to, the calculations for this are beyond the scope of this video, but here's the equation for how many items we're going to have to visit, how many comparisons if we have linear probing. Let's add that to our graph. Whoa! Whoa! It's going to go way up, up, up. In fact, it even starts at 1, interestingly enough. We don't have to, we could get a list and it could be empty, and we're not going to compare any items, but we at least have to compare one item to see if it's there. And notice it goes high and it goes up and up and up. So you can see for linear probing, when we get about half full, it's about to take off. And so when our load factor is more than half, then we want to rehash, okay, to save our efficiency. Also, quadratic probing here, a little bit simpler formula, and it does better. In general, it does better, but still not good. And notice we could maybe push it a little further, maybe 2/3 full for quadratic probing, but certainly we're going to need to rehash before too long, and especially well before separate chaining. Okay, so that's unsuccessful searches. Now let's talk about successful searches. So if it's a successful search and we're doing separate chaining, so our hash table is a list of pointers, or a list of, it's an array of lists, then we're going to traverse that list looking for it. And by definition, because it is successful, we're going to find it in the list. Well, on average, we're going to find it about halfway through the list. So we know we need to do at least one comparison because we found it. And on average, we're going to go halfway through the list. Well, how long is the list? Well, on average, it's alpha in length. So halfway through on alpha. Let's add that to our table. Okay, successful searches. Okay, so we do at least one, and it goes up linearly halfway through the list. Okay, looks pretty good. Now let's look at linear probing and quadratic probing here. We add those, in successful searches, they're doing better here for linear probing and quadratic probing, but they go up, and they go up quickly once they start going up. Okay, so we need to watch out for that, and we need to rehash when it gets too large. But in general, successful hashes are going to take less time than unsuccessful hashing. Okay. Now let's talk about some of the disadvantages of hash tables. We've talked about the advantages with the excellent insertion and searching time, a big O of constant in general. But hash tables are not a general purpose storage retrieval data structure. For example, imagine if you were to traverse all of the items in sorted order. How would you do that? You'd have to go through, find the smallest one, visit it, and then you'd have to go through and find the next smallest one, etc. Very painful, not meant for it. It can be very costly to do that. Would not want to do it. I think the best thing you could do is, if you had to do it, was go through your entire hash table and dump them to another data structure that does have it sorted, like a tree or something like that, or a heap or something along those lines. Another operation that'd be difficult with hash tables is finding the minimum or the maximum search key in the hash table. That's similar to a traversal, or in general terms, a range query. These are all difficult things to do with hash tables. Now, they can be done, but it's not natural. And so if you need these operations, hash table might not be what you want. The other thing is, we do have that rehash in there, which can pop up at unknown times, giving you a little bit erratic timing. If that's important, then maybe hash tables aren't for you. Otherwise, they're awesome. You should use them. Well, that wraps up the video.